Okay, we've now learned how to solve standard maximization problems in 4.1, and in 4.2 we learned how to solve minimization problems with standard max constraints, that is all less than equal to a non-negative number constraints, and how to solve standard minimization problems. Those are minimization problems with greater than equal to constraints. We're now ready to move on to solving non-standard problems, and we will start with non-standard maximization problems. What is a non-standard maximization problem? Simply put, a maximization problem that cannot be written as a standard max. So you'll see greater than equal to non-negative number constraints. You'll see less than equal to negative number constraints. You may even see some equations. Okay. A problem that has both greater than equal to and less than equal to constraints is a linear programming problem with mixed constraints. So when you hear mixed constraints, you know there's mixed up, greater than equal to and less than equal to. I will remind us that all variables, including the slack variables, are non-negative. In fact, only the objective function variable P can be negative in a final tableau. Keep in mind we do turn our minimization problems into maximization problems, so technically C could also be negative. So in a nutshell, the bottom row, far right column, is the only place that's allowed to be a negative in the constant column, is the bottom. All right. So we're going to take a look at this non-standard maximization problem. Oh, it is non-standard because greater than equal to 88 here in the second constraint. We're going to solve this graphically since there's two variables, and then we're going to look at the algebraic approach with our simplex method. I have graphed both lines below and found our feasible region. We have the constraint 12x plus 8y less than equals 144, and the constraint 4x plus 8y greater than equal to 88, producing this feasible region. Of course, we do have x and y both being greater than equal to 0. We do have a bound feasible region, so we know there is a solution and it will exist at one of the corners. 0, 11, plug that into the objective function and we get a p-value of 55. Plug 0, 18 into the objective function and we get a p-value of 90. Plug the corner point 7, 7.5 in to the objective function and we get a p-value of 93.5. So clearly p equals 93.5 is our optimal value, and this occurs at x equals 7, y equals 7.5, and that is our optimal solution. So now that we know what the answer is, the optimal value and optimal solution, let's take a look at how to do this algebraically using our simplex method. You will want to keep this handy because we will refer to it, so I suggest just leaving it off to the side for right now. Okay, so at the top of the next page, I'll slide this down so we can see it, we have our non-standard maximization problem. The first step is to rewrite the maximization problem and all maximization problems so that they have all less than equal to constraints. So we'll just multiply both sides by -1 and make that constraint -4x minus 8y less than equal to -88. That's the only constraint we needed to change, so we can rewrite our maximization problem. Maximize p equals 8x plus 5y subject to 12x plus 8y less than equal to 144, and then the less than equal to form of the constraint, -4x minus 8y less than equal to -88, and of course x and y are still greater than equal to 0. Now that we have the maximization problem in all less than equal to constraints, we can introduce the slack variables and create our system of equations with the objective function at the bottom. So that creates the first equation, 12x plus 8y plus the slack variable 1 equal to 144. Then negative 4x minus 8y plus slack variable 2 equals negative 88. And our objective function at the bottom, all the variables brought over to the left, same side as p, negative 8x minus 5y plus p equals 0. Once we have the system, we can then enter in our initial tableau. And yes, eventually you will be able to skip over this if you haven't already gotten to that point. 12, 8, 1, 0, 144. Negative 4, negative 8, 0, 1, negative 88. Negative 8, negative 5, 0, 0. And here you will notice I am leaving off the P column because we've said numerous times before that column never changes. It stays active with the 1 in the bottom. So I'm just not going to write it anymore. Alright. We will see in every initial tableau the active variables are always the slacks, meaning x and y are equal to 0. We know S1 is equal to 144, and we know S2 is equal to negative 88, which is a problem because all of our variables are supposed to be non-negative. The fact we have a negative value for one of our variables tells us we are not in the feasible region. And since x and y are both equal to 0 right now, if we look back at our graph, the origin 0, 0 is definitely not in our feasible region. So this is making sense. So the real question is, how do we get to our feasible region? And then how do we solve? The good news is once we get to the feasible region, we just continue on like it's a standard max problem. So how do we get to the feasible region? We have 3 steps to follow, 1, 2, 3, and then 4 is just repeat these until we do get to the feasible region. So we know we're going to be in the feasible region once there's no negative constants. So how do we get there? Step 1. Find the first negative entry in the constant column. So find our first negative constant. Alright, negative 88 is our first negative constant for this example. In the same row as that negative constant, we want to find the most negative entry to the left of that constant. Not any, but most. And we'll revisit that idea later. So the most negative number to the left of negative 88 is negative 8. That will be our pivot column. To find our pivot row, step 2, we do the ratios as always. The constant divided by the entry in the pivot column. So 144 divided by 8 is 18. Negative 88 divided by negative 8 is 11. Now, how do we choose our pivot element here? Very similar to before, the pivot element is going to be the smallest positive ratio. So we're not going to pivot on non-negative ratios when we're not in the feasible region. We're only going to pivot on positive ratios, specifically the smallest positive ratio. So 11 is the smallest positive ratio. That means our pivot entry is this negative 8. Okay. So we perform that pivot, and after performing the pivot, if there's still negative constants, we repeat step 1, 2, and 3. And we keep repeating those steps until there are no negative constants here in the center section. So let's do our pivot, and the result of doing our pivot is this table down here. So before we look at that result, let's do note, you could have a tie in your pivot ratios for the smallest positive ratio. So if there is a tie, make sure you always choose the pivot row to be the row with the negative constants. That is, if your tie is between a row with a negative constant and a positive constant. Sometimes the smallest positive ratio is attached to a row with a positive constant, and you just have to go with it. But if there is a tie between a negative constant row and a positive constant row, you always choose the negative constant row to be the pivot row. If your tie for the smallest positive ratio is on two rows with a negative constant, you just pick one. I tend to go with the top one, but you can just pick one. Okay? The important thing is when there's ties, pivot in the negative constant row if that is one of the ties. So we now can look at our tableau. We see there's no negatives. We can identify the active variables as S1 and Y. S1 equals 56. Y equals 11. X is inactive, so X is 0. Okay. So labeling the active variables, S1 is active in row 1, Y is active in row 2. Do we have any negative constants? No, we don't. Which tells us we are in the feasible region. We are in the feasible region. So our basic solution, X is inactive and equal to 0. Y is active and equal to 11. Okay. So now that we are in the feasible region, what do we do? Well, let's take a look at the next page and see exactly what we're going to do. So here at the top, it's the tableau we had at the bottom. We are now in the feasible region. So we proceed on as if this was a standard max. We get our pivot column by searching for the most negative number in the bottom row. And if there are no negatives, we're done. But we do have negatives. The most negative is negative 11 over 2. That gives us our pivot column. We do the ratio as before, making sure smallest non-negative ratio is what we'll pivot on. So 56 over 8 is 7. 11 over 1/2 is 22. Smallest non-negative ratio is 7, so that'll be our pivot entry. We'll perform our pivot and see what we have. This is the result. We'll notice no negatives. And there's also no negative constants. So this is a final tableau. And we can now read the answer. Of course, it should match up with what we did graphically. Optimal value, 93.5. Optimal solution is the 0.77.5. Okay. So we know this is a final tableau because there's no negatives in the bottom, and also there's no negative constants. Remember, if you've got negative constants, we've got to get rid of the negative constants before we worry about negatives in the bottom row. That's what we went through. Okay. Now, I do want to point something out as to why we're choosing the most negative entry to the left to be our pivot. Based off what the book says, it does say you can find any negative entry to the left. So, if we were to choose the -4 to pivot on, or to be the pivot column, I'm sorry, we do our ratio. 144 over 12 is 12. -88 over -4 is 22. 12 is clearly smaller than 22, so we would actually pivot up here on the positive constant row. Again, that is possible. You always stick with the smallest positive ratio no matter what row it's attached to. So if we're going to pivot here, 12, where the 12 is, we divide this whole row by 12 and get a 1. We would declare that column. And when we divide by 12, this becomes a 12. X would be active, Y would be inactive, so we're at the point 12, 0. And when we look, the point 12, 0 is not in the feasible region. We would have another negative constant. Specifically, we would have a negative 40 here. And I'll let you perform that pivot on your own time to see that you would still have a negative. Okay. Also, if you'll note, after our first pivot, when we chose the most negative entry, we got to 0.11, which is in the feasible region. Okay. So while we're choosing the most negative, choosing the most negative of these guarantees this ratio to be as small as it possibly can. And if this ratio is as small as it possibly can, we are much more likely to pivot in this row, which is what we want to do when we have a negative constant. Pivot in the row with a negative constant. That's how we get rid of the negative constant. But again, you have to follow the rule, no matter what row that's attached to. Okay. So that's how we get into the feasible region. We will be pivoting on negative entries until we get into the feasible region. Once we're in the feasible region, it's a standard simplex. We do not pivot on negative numbers. We do not pivot on 0 ever. In fact, the only time we're pivoting on negative entries is when we are not in the feasible region. So I have another video that will go through 2 more examples. This is just the first one. Hope that works. We will have these 3 steps. We will be repeating them quite a bit. So go on to the next video to get the examples, or the next 2 examples.